the first talk we'll have is from Mr. Raoul Correa, who's right here. He's going to tell you a little bit about quantum dots. So I'd like to ask you all just to give a welcome to Raoul.
Hi. Is this loud enough? Can you guys hear me in the back? I'm talking to you guys. Take a seat. Come on, you're going to learn something right now. Excellent. All right. So my name is Raoul Correa, and I'm a graduate student at MIT. And today, I'm going to tell you a little something about quantum dots, these wonderful, fantastical, colorful little crystals. So, before I get into the nitty-gritty of what quantum dots are, I thought I'd mention a little bit about myself. I'm Indian originally. I was born in Bombay, in India. And when I was about 8, I actually moved to Auckland, New Zealand, and I grew up there for about 10 years. And then, I basically spent time hiking the Lord of the Rings mountains and chasing sheep and all that kind of fun stuff. And when I was 18, I moved over to the sunny shores of California, where I'm sure we all wish we were right now. And I did my undergraduate at Berkeley for 4 years in chemistry. And then I hopped over to the better coast, and now I'm in Cambridge, and I'm in my second year doing my PhD in chemistry. And a little bit more about myself, I just like science. I really do. It's something which has fascinated me since I was about as big as you guys, all the way in the back. It was something which I was always very curious. I always ran around messing with things. Mom and Dad were yelling at me all the time. But now I get to do this as a career. This is what I do. I mess around with stuff, and people don't yell at me anymore. And it's great. It's just absolutely fantastic. And what I'm doing here today at the museum is to kind of dispel this myth that scientists look like this. So while I do have the glove, and I do kind of have the goggles, I don't have the white hair, and I don't really have this frazzled, evil-looking look. All right? What I'm hoping to do at the Museum of Science is to kind of communicate some of the more esoteric, these crazy things we do in the in our research labs at MIT and Harvard and all these other universities in Boston, kind of bring them to the public to kind of show the kinds of things that we do in a very approachable way. Because at the end of the day, science is fun, and a lot of these things are just really easy to understand, and they're just neat. So hopefully that's my goal today, is to try and convince you that these things aren't that hard to understand, and science is worth pursuing. And just to give you a little perspective, this is really what scientists at MIT do. We don't, we work hard during the day, but on weekends we are known for our volleyball games and having, basically just a good time. And in fact, a lot of collaborations spawn from things like this, where we have biologists, chemists, physicists, just hanging out, having a good time, and just learning from each other. And if you look at me, I'm over there in the corner looking very eagerly at the ball. So, I promised to tell you guys a little bit about quantum dots, so let me cut to the chase. What exactly are quantum dots? And for the rest of the presentation, I'm going to refer to them as these QDs. Quantum dots are really just very, very small crystals. And it turns out when you make them this small, they start having all these really weird and unusual properties. So for example, does anyone in the audience happen to know of any crystals that are very sweet? Does anyone know any crystals that are very sweet that we add in sugar? All right, you guys in the back. You're gonna have to yell it for me. Sugar, perfect. Sugar is a perfect example of a crystal. All right, what about a crystal that we might form with water if it gets really, really cold? Any idea? Okay, yes? Ice, perfect. Ice is another kind of crystal. And this is really cool because we're used to thinking about crystals as being these big, big objects. It turns out that you can also form crystals that are really, really small. And this is the kind of stuff that I'm interested in. So just to kind of give you an idea of how big or how small these things are, I have this little scale right here. So the crystals that I work with are roughly 1 or 2 nanometers big. So a nanometer is kind of a hard thing to understand, but we kind of have an idea of what 1 meter is. It's about yay high and yay big. And we have an idea of how big the sun is. The sun is huge, and it turns out it's about 1 billion times something of this length. So just imagine it now in the opposite way. Instead of thinking of something as 1 billion times bigger, now we're dealing with crystals which are 1 billion times smaller. And it turns out that when you go to this very, very small regime, you start seeing all these really, really neat properties. And I hope to kind of share some of those properties with you guys today. So, why are they important? Here I've kind of highlighted a few of the technological aspects of why quantum dots are important. So on the left-hand side over here, we have quantum dots, these tiny, tiny little crystals, which have been used to create very efficient LED displays. So for example, I'm sure there are a lot of dads in the audience who wish they had an LED or plasma TV for that matter. But the problem is, for example, with a plasma, even something like this, when you walk really close to it, you can feel the heat coming off it. It's just an extraordinary amount of energy being used. What we're hoping to do is to actually use quantum dots to make these things use less power and become more efficient, and at the end of the day, just save us a whole bunch of money. So that's one particular example. On the right-hand side, we're trying to use quantum dots to actually make solar cells as well. And I'm pretty sure we're all comfortable with the fact that these days, we really want to move towards renewable sources of energy, right? We don't want to deal with these same kinds of fossil fuels which are using upwards of 80% of our total energy costs at this point. So, on the left-hand side, we have electricity going in and light coming out in the form of a TV. On the right-hand side, we have light coming in and electricity coming out. And at the end of the day, it turns out that quantum dots, these tiny, tiny little crystals, are very good for being able to turn light into electricity, as well as turning electricity into light. From a biology point of view, quantum dots, or these tiny, tiny little crystals, are very good at helping us see these tiny, tiny little things. So over here, what I have are different kinds of cells, and these cells happen to be cancer cells. And a few years ago, probably about a decade ago, we really couldn't image these kinds of things with this much amount of detail. And the reason is, the kinds of stainings, these fluorescent particles and things that they would use back in the day were just not as efficient. They just could not produce these very clear images. And it turns out now when we use quantum dots, these images are just so much more efficient, and they're just able to produce just very crystal clear pictures of what exactly is going on inside the cell.